In the Convert channel, I try to turn every challenging industrial problem into something smart and simplified version. Hello and welcome into vertical two-phase vessel sizing procedure by Excel sheet. We need to consider the design and the concept behind the vertical two-phase sizing procedure. I use a binary article for our vessel sizing. This is our actually article that we are going to use and take into our sizing procedure. So in this case, I provide a feed inlet of the gas hydrotreating unit that goes into the vertical vessel, that its thermodynamic condition are provided on the table on the right hand of the window for the liquid and the vapor. Total mass flow and volumetric flow are provided, as you can see, respectively. I inserted this value into the Excel sheet. I highly recommend you to stop the actually tutorial and insert this value in the proper unit to make sure that you are going to come with me step by step. So I will jump into the design procedure and the concept behind of each step. I will talk about the low liquid level, distance, field operation time, vapor space high. So let me firstly talk about the hold up time and search time, which is really crucial according to the Monary article. This is a typical range of control range that is recommended by Shell design practice. That its simplified version are given right here. For the hold up time and the search time, I will talk about these values firstly, and then we jump into other section, which is much more easier than this part. So let's go to the hold up time and the search time according to the Monary article. For the hold up and the search time, as you can see, where your separators serve as a feed column, feed to column 5 and 3 minute can be considered respectively. So summation of these two values, I will insert summation of these 3 and 5 minute, which is equal 8 minutes as summation of this value as a whole log time and the search time. So for velocity and diameter, internal diameter of the vessel, we need to get back to the Monary article and then learn the concept behind of each step, and then I will talk about actually sizing procedure of this part as well. So the exact K value is really dependent on whether you have mist eliminator, vane pack, or whatever internal devices you are going to use into your vertical vessels. But in this case, I do not use any mist eliminator, and that K value typical range in this case is equal 0.05 meter per second. If you need the exact value of the K, you can actually refer to the Monary article. For different pressure ranges, you can find the formula or correlation just right here and find the exact value of each. Each different ranges that you are going to work with. So let's take this value as initial guess. So for the vertical velocity of the vapor according to the Monary, again 75% of this formula is considered as the velocity. So we have the K value is velocity of the liquid, vapor, and the vapor again we can easily calculate the critical velocity, then multiply this by 0.75 and find the acceptable velocity within the vertical vessel. So let's jump into the Excel and find the exact value of this. 0.75 or 75% of this value, which is K times square root of difference of actually liquid density and vapor density per vapor density. Then close up the bracket and hit enter. As you can see, we have gained acceptable velocity within the vertical vessel. So for internal diameter of vessel, you can actually I highly recommend you to look for the line sizing procedure. If you haven't watched that tutorial, I highly recommend you to watch that tutorial. Firstly, because it's really is the same procedure and the concept behind of these two sessions are the same. So let's jump into calculation of this parameter as well. I have talked about this parameter which is SQRT of 4 times vapor flow rate. Just make sure that divide this number by the 16 to 10 cubic meter per minute into cubic meter per second, then divide this number by 3.14, then divide again by the velocity which you have gained earlier. So cross-sectional area, you know the formula. I do actually consider that you do know the exact formula, which is 3.14 times internal diameter of vessel powered by 2 per 4. As you can see, 2.1, about 2.1 actually meter is our value. I have talked about the summation of hold up and the search time according to the manual article. Let's jump and calculate the volume between these two actually level that is given right here. That is the pre-alarm, actually the low liquid level to the pre-alarm, which is the high alarm on the DCS. So consider this value that this cell can be calculated by multiplication of this cell and liquid flow rate. I missed the multiplication sign, that its exact value can be determined by this way. So we have the volume and the cross-sectional area, and we can easily turn it into the distance. You can see 21 meter is the distance between low liquid level to the high, which is known as the pre-alarm on the DCS. So we need a slight time. If you can skip this part if your feed that goes into the vessel is within 1 phase. If it's totally liquid or vapor, you can skip this part and then jump into this part that I will talk about later. But in this case, we have a two-phase flow. I need to consider 5 seconds as a slack time, which is highly recommended according to the Excel, actually Exxon. I mean, just, sorry, design practices, and divide this number by 60 to turn it into a minute. A slack volume, you again need to consider the total flow rate of uh, liquid and vapor times this slack time. Just make sure that you multiply this value by summation of these two, liquid and the vapor flow rate, because it's really dependent on the liquid and the vapor and this time. It's maybe actually level on the top of the vessel will be accommodated according to the summation of these two values. So, and again, apply the same procedure. We have the volume and the cross-sectional area. We can find the slack high. I have talked about this process, but if you have a single phase failure, you can skip this procedure and you can easily take this distance as 0 meter. So operator intervention time or operator response time is known as actually high alarm to the high alarm, which is known as a trip, where your transmitter sends signals to other equipment or whatever it is to prevent your vessel from damaging. So for this case, according to the shell design practices, that is highly recommended for the vertical vessel from high to actually from high to high you can actually or locate such that dress or blah 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 5 minutes for action outside the control room. For the field operator on the site, you can consider 5 minutes according to the between 1 and 5 minutes. 5 minutes I will choose the 5 minutes, which is the worst case scenario in this case, as the operator response to prevent overfilling of our vessel. So in the intervention volume, we actually have the times that it takes to accommodate that part times liquid inlet flow rate that we have talked about earlier. So then again, do the same procedure. We have the volume, divide this value by the cross-sectional area. We have the high from the actually high into high level, which is from the pre-alarm level to the high level that our signal is going to send to other equipment to prevent our vessel from damaging, overpressuring, or in this case, overfilling of the liquid or whatever it is. So we have calculated this part distance as well for the vapor space. Its typical ranges in many cases. Let's just take this as an example. 20% of internal diameter of our vessel. That is highly recommended. In this case, for low liquid level, we can't talk about it too much, but it's out of our time. We do not have enough time to save time. It's really dependent on whether you have actually pump at the bottom of the liquid or not. If you have the pump, you should refer to the vendor document and find the net positive suction head, which is required or recommended, actually suggested by the vendor. If you do not have any pump, you can consider 0.15, or in some cases I have seen that some engineers take this value as 0. Actually 3 meter. I will consider, for example, 0.3 meter. Actually, it's really dependent on that, on your procedure, whether that you have the pump at the outlet of the liquid or not. For the total length is summation of this value, which is low liquid level, hold up and surge time level, field operator action time, that is 5 minutes. We consider 5 minutes according to shell design practices at 20% of inner actually vertical vessel diameter, which is highly recommended. So the summation of this yellow cell is our vessel length. Just sum this up as well. 36 meters. So L per T is this cell per internal diameter of vessel that we have calculated earlier. But L per D ratio is 22, which is not acceptable. In many engineering and document or design practices or standards, its recommended range is something between 2 and 5, in some cases 6. That 22 is too much for our vessel. That is not the proper L per D actually ratio. So we need to increase the internal diameter of our vessel to make sure that we have much more space to accommodate much more volume of the liquid. To decrease this value, it is summation of actually each each of this value affect the length of our vessel. So I will increase the calculate the internal diameter of the vessel. I will take consider for example 20 meter. As you can see our LE ratio decrease. I will consider 2.6. As you can see it's going to decrease as well. I will consider 2. For example 8. That is really acceptable. 4.7, that is within the acceptable range. So we can actually report this value, which is 30 meter and for the length of the vessel, and the internal diameter of the vessel, which is 2.8. That is it's a kind of acceptable, but to be honest with you, it really depends on your procedure, or every vessel, or whether it's vertical two-phase or horizontal two-phase or three-phase or whatever it is, it really has its own actually concern. You need to take into account every concern that affect your sizing procedure. Just take this tutorial content as a way to lead you to the vessel sizing procedure. Okay, if you found this tutorial helpful, please subscribe my channel and share it with your friend. I will share the money article with you. Do not actually be worried about this article. That is really highly recommended for you to read this article. That is really useful in vessel sizing. Okay, thank you. Have a good time. If you have any questions, just let me know in the description below. Have a good time. Bye bye.